Okay, today we carry on with BJT amplifiers. We're still busy with the common emitter amplifier. This lesson is going to be about voltage, current and power gain. Alright, firstly we're going to have a look at voltage gain. Remember, I want you to have your textbooks ready so that you can mark in the textbook what is important for you to study, especially. Alright, if we look at figure 614, you were introduced on the voltage gain of a common emitter amplifier in Electronics 1. There was a small section on the amplifier in chapter 5, just an introduction. So this was basically also mentioned there. But anyway, we can see that the AC voltage gain expression for the common emitter amplifiers developed using the model circuit in figure 614. The gain is the ratio of the AC output voltage at the collector, VC. You can see there on figure 614, to the AC input voltage at the base, VB. Alright, so if you will follow me in your textbooks where it says voltage gain is then V out over V in. Remember, voltage gain is the ratio, It's the output voltage over the input voltage. I want to see how many times that I amplify the input signal, which is VC over VB. We also notice in the figure that VC is equal to alpha AC IE RC and VB is IE R accent E. So if I substitute in the formula of VC over VB, I get IE over RC divided by IE over R accent E. The two IEs cancels out and I remain with the voltage gain. Voltage gain is then equal to RC. Voltage gain is equal to RC. Remember, that is a DC quantity, over R accent E, which is the AC emitter resistance. Alright, that is the basic formula for voltage gain of a common emitter amplifier. You will also see later that this is the maximum voltage gain that I can get from an amplifier. But that is not necessarily the voltage gain that you're going to get from a specific amplifier that you will be given in the exam or in the lab or whichever amplifier you might work with. Remember, I told you earlier with the previous lesson that I always have to go and look at the specific circuit that I'm working with, which components are included and so forth and so forth. But I'll point it out as we carry on. Alright, very important section on the next page is the attenuation. We also basically had an introduction to that in the previous lesson. But I want you to underline that second paragraph where it starts attenuation, boldly printed. Attenuation is the reduction in signal voltage as it passes through a circuit and corresponds to a gain of less than 1. Alright, so if I go and look at figure 615, I can see here the attenuation is mentioned. Then also voltage gain is mentioned and also overall voltage gain is mentioned. But this attenuation part here, we also basically discussed that. Remember when we talked about the AC analysis of the amplifier in the previous lesson, we had to simplify the circuit. Now firstly we had to take our amplifier circuit and we drew the AC equivalent circuit. Remember, because the way that the capacitors act and the DC supply, which all of them acted as shorts. Can you recall? Alright. So then I simplified the circuit and I saw then, as I can see in this figure as well, that R1 is in parallel with R2. I've also seen that I have an RS. It's not always given, but if it is given, then I have to calculate the attenuation, but I will get back to that. RS, of course, is the source's internal resistance. It's not a series resistor. Alright, and then I've also seen in this specific case there is no RL, because if there was an RL, then RC also would have been in parallel with RL. Nah. But now I can see it's only RC on the output, so I can see in this specific circuit no load is connected. Nah. That's why I always said you always have to look at the specific circuit that you work with. You can't include an RL if there's not an RL given in the circuit. Nah. Alright, then we've also discussed when we simplify that, if there's an RS, what happens? Can you remember? We looked at this part of the circuit here, which was a simple series circuit with two resistors, and the two resistors acts as what? A voltage divider, no? A voltage divider for my source voltage. Remember my source voltage? Eventually to become VB, which I want to amplify, and amplification, and then the output is taken at VC, no? And then we've also seen now that the gain is the output over the input. Alright, and then we simplified the circuit, it's RC over R, X and T. But in the beginning we had output signal over input signal. Alright, now where does the attenuation part come in? As soon as I have this RS, I can see that it acts as a voltage divider for my input signal. So if I go and refer back to the sentence that I've just read, it says attenuation is the reduction in signal voltage as it passes through a circuit and corresponds to a gain of less than 1. So what I'm saying is a voltage divider gives me a ratio of less than 1, so it's going to reduce the signal because of the voltage divider action that takes place. Né? Alright, we can read that example there in the textbook. It says, for example, if the signal amplitude is reduced by half, the attenuation is 2. Now this is a bit confusing. I don't really agree with the guy that wrote the book, because he's just told us that the gain corresponds to a value of less than 1. But you will see here in the end, what he does, he gets the reciprocal of that number, which will give you a value of less than 1. If you go and look there at that formula which says attenuation is equal to Vs over Vb, which to me is actually the wrong way around, which is Rs plus R in total divided by R in total. Of course, that is not going to give me a value of less than 1, but you will see then he gets the reciprocal of that. The next sentence says the overall voltage gain of the amplifier is the voltage gain from the base to the collector times the reciprocal of the attenuation, which to me is a bit confusing, but let's stay with the book. I tried to teach the students in the past that the attenuation, as he says here, also corresponds to a value of less than 1, but right through the book he's changed it. It gets the reciprocal, so it becomes less than 1. So let's rather stay with the book so that you're not confused. Anyway, let's carry on with that example. He says then, the attenuation is 2, which can be expressed as a gain of 0.5 because gain is the reciprocal of attenuation. But for me that was superfluous. I would have said 0.5 right from the beginning because attenuation is 0.5. So you can approach it that way as well, or you can approach it the way that the book is using it. He says, suppose a source voltage of 10 millivolts input signal and a source resistance combined with the load resistance results in a 2 millivolt output signal. In this case, the attenuation is 10 millivolts divided by 2 millivolts, which is 5. That is, the input signal is reduced by a factor of 5. This can be expressed in terms as gain is over 1 over 5, which is 0.2. All right. Yes. You can use, as I said, I'm going to repeat again, you can use as they say here in the book, or you can use as I prefer to do, that it should be R in total divided by Rs plus R in total, because then I can see that will give me a value of less than 1. Alright. Anyway. Anyway, again, I want to stress the fact that if RS is not available, then of course I cannot calculate attenuation. So if you have a problem and they don't give you the value of RS, then of course you cannot calculate attenuation. Then you can only calculate voltage gain. Alright, voltage gain. I can only calculate the voltage gain, as we've seen that the base formula for this, and it will apply to this specific circuit as well, is RC divided by R accent E. But if I do have RS and I can calculate attenuation, then I will go and calculate the overall voltage gain. The overall voltage gain is going to be the attenuation multiplied with the voltage gain to get the overall voltage gain right from my input signal up to VB. Okay, I mean to the output VC. Okay, that's the overall voltage gain. But I can only calculate overall voltage gain if the value of RS is available. So in the lab, the amplifier that you're going to build there as well, you're going to use the signal generator as your input signal that you want to amplify, and that information is available. You will see on the output of the audio amplifier or the signal amplifier actually, it's written there what is the value of RS, the output resistance of that, or the internal resistance of that device. Alright, then the next section, the effect of the emitter bypass capacitor on the voltage gain. Please also mark this because this is the only place where they show in this textbook how to determine the value of C2. But before we get to this specific problem in figure 616, the effect of the emitter bypass capacitor on the voltage gain. You can mark those two paragraphs at the bottom of page 268. This is very important. The first important thing is, remember I told you already, we're looking at the AC signal. AC signal, because for AC this capacitor acts as a short, the AC signal is going to be connected to AC ground. Other words, RE doesn't feature in my calculations for my AC signal. That is why that capacitor is called a bypass capacitor. Now remember, we just said that the voltage gain is equal to RC over R accent E. Where's R accent E? That's the AC emitter resistance in the internal, in the transistor. Why is this formula in this specific case true? Because I am bypassing RE. If that capacitor wasn't in the circuit, what do you think will happen to my voltage gain formula? I will have to include the value of RE. And what do I know about the value of R accent E? Small. We said normally I would say between 5 and 20 ohms. Small. What do I know about the value of RE? I can see it's fairly large. In this case, 560 ohms. So what do you think is going to happen with the voltage gain of this specific amplifier if I do not have the bypass capacitor? It's going to go way down. So my voltage gain is going to become much lower. Alright, so that is the effect of the emitter bypass capacitor on the voltage gain. So if I do not have a bypass capacitor, then I have maximum voltage gain. Maximum voltage gain for a common emitter amplifier is RC over R accent E. Small resistance below the line. RC, I can see also, big resistance, 1 kilo ohm. Alright. So, if I do not have the bypass capacitor, then of course my voltage gain becomes much lower. Anyway, the last paragraph there deals with, it's discussed in example 6.4, but let's have a look at that first. It's to calculate the value of C2. Let me just erase here. Clear it up a bit so that we can see again. You understand this part? It would be nice if you say yes or no. Anyway, the value of the bypass capacitor, you can underline this is important. The value of the bypass capacitor must be large enough so that the reactance over the frequency range of the amplifier is very small, ideally 0 ohms compared to the value of RE. A good rule of thumb is that XC of the bypass capacitor should be at least 10 times smaller than RE at the minimum frequency for which the amplifier must operate. Double underline, because you're going to miss that. What does it say there? It has to be 10 times smaller than RE at minimum frequency. Because if you don't note that, you're going to make a mistake, ne? Alright, so I can see the 10 XCs should be smaller than the value of RCs, the formula there. So let's have a look at the example. On page 269, the example says, select a minimum value for the emitter bypass capacitor C2 in figure 16 if the amplifier must operate over a frequency range from 200 Hertz to 10 kilohertz. Okay, already I read something in the previous chapter, or the previous, not the previous chapter, the previous paragraph, which I should note, which is what? Minimum frequency, ne? Okay, so I must remember that already. Let's have a look at the solution. The XC of the bypass capacitor C2 should at least be 10 times less than RE. So I take the value of RE divided by 10. And in this specific case, I can see it's 56 ohms. Now it's 560 divided by 56. By 10 gives me 56 ohms. Alright, then determine the capacitance value at the minimum frequency of 200 Hertz. And you are familiar with this formula. It's the formula for capacitive reactance. I just jiggled it so I can get the value of C2 out of it. So C2 then is 1 over 2 pi f xc 2, which is 1 over 2 pi 200 Hertz, minimum frequency. And then of course my xc for 2 I calculated should be 10 times less than the value of RE, which is 56. And I get a value of 14.2 microfarads for this specific problem. Okay, so two things that I have to be careful to watch out for. The rule of thumb, XC should be 10 times less than the value of RE. And of course that I should calculate this value at minimum frequency. Alright, just below example 6.4. Voltage gain without the bypass capacitor. Here you can mark it. I've already told you and I showed you on the board here. You can see how my formula, my equation changes. Now it's equation 6.6. If I do not have the bypass capacitor, as I've seen here, then my formula changes to equation 6.6. That's why I say you always have to look at the circuit that you work with. So now AV, voltage gain, is equal to RC divided by R accent E plus RE, because RE is now not bypassed, not bypassed. If I have a look at the, just keep these values in mind, it's quite interesting. Example 6.5, because they use the same circuit. The example from this formula is without the bypass capacitor. I can see I only have a voltage gain of 1,76. 1,76 because I did not bypass RE, so all of RE is then included in my formula. If I turn the page and I go and look and I say, alright, now I'm putting the bypass capacitor in, you have a look at the difference in the value there. You can see now it is maximum voltage gain. Remember, this is the formula for maximum voltage gain. is RC divided by Rx and E. Now I have a voltage gain of 152. Quite a difference from 1,76, né? 1,76, but unfortunately there are other factors that we have to keep in mind, which we will discuss in a moment. Firstly, let's have a look what else has an influence on the voltage gain. The effect of the load on the voltage gain. Remember in our examples now we didn't have a load resistor, né? We all saw that. So in this case now I am including a load resistor, so what is going to happen? I have to calculate this value RC, which is R small c, né? In a lowercase letter indicates that is the resistance that the AC signal sees, so it's going to be RC in parallel with RL. Then I have to calculate that value. As soon as I have RL in my circuit, then I have to calculate, because I've seen when we drew the equivalent circuit for the AC amplifier for the AC signal that if I simplify it, RC is in parallel with RL. How does this influence my voltage gain? Let's have a look. So now voltage gain, remember we said maximum voltage gain was equal to R, capital letter C, R, X and E. Né? Then I also saw, okay, if I don't bypass, this was in that example, gave me a value of 152. Né? If I don't bypass, then I have to include RE as well. Né? Then it came down to, in this specific example, 1,76. Alright, so let's go back again to our maximum voltage gain. Let's go back to our maximum voltage gain, but now I have RC in parallel with RL, which gives me R lowercase c. Né? So let's change this to R lowercase c. Success. Okay, so that's a lowercase c, which is now RC in parallel with RL. Né? So if I go and look, this is the same example, or the same circuit that we're looking at, example 6.6. RC in parallel with RL gives me now a value of 833 ohms. So remember previously, in the previous examples, RC was equal to 1 kilo ohm, the output resistance. Now the output resistance changes to, in this example, to 833. How is that going to influence my voltage gain? Even if I use the formula for maximum voltage gain, I can see now it's 833 divided by 6,58 ohms. And now it's only 127. Remember the previous one it was 152. So already I can see just by using load resistor. The load resistor in this case was a 5 kilo ohm load resistor, and it brought down the total output resistance then to 833. But now can you imagine what is the impedance or the resistance of a normal speaker that we use on an amplifier? Do you know? It's normally 8 ohms, isn't it? Normally 8 ohms. Now can you imagine if I have a resistor of 8 ohms in parallel with a resistor of 1 kilo ohm, what's the total resistance going to be then? What's the output resistance going to be then? It's going to be less than 8 ohms. No? It's going to be close to 8 ohms. But now can you imagine if I have 8 ohms divided by, what was that value of R, X and E? 6,58. Can you see what's going to happen to my voltage gain? But that's another problem that we will address. Okay? So just keep in mind, my load resistor has a huge influence on my voltage gain as well. Okay, that's what I want to point out to you here. Alright, now it brings me to my next point that I wanted to talk to you about, the stability of the voltage gain. That's, remember I told you that I can use this formula of voltage gain. This is the maximum voltage gain for this amplifier, né? RC over R, X and T. But remember I told you always have to look at what the circuit looks like that you're going to work with, né? But before we get to figure 618, let's read some, and I want you to mark some of these sentences as well. Stability is a measure of how well an amplifier maintains its design values over changes in temperature or for a transistor with a different beta. We've discussed that already as well. Ne? We know that beta is not constant, influences by collector current and temperature and so forth. Although bypassing RE does produce the maximum voltage gain, there is a stability problem because the AC voltage gain is dependent on R accent E, since AV is equal to RC over R accent E, totally dependent on R accent E. Ne? And listen here, that is the important part. R accent E depends on IE and on temperature. So it changes, it doesn't remain constant. This causes the gain to be unstable over changes in temperature because when R accent E increases, the gain decreases and vice versa. I can see that in my formula. Ne? If R accent E increases, then of course the value below the line becomes larger, voltage gain is going to drop and vice versa. Which I don't want. I don't want that. I want a stable amplifier, constant volume. I don't want to change it automatically. Ne? Alright, so with no bypass capacitor, the gain is decreased because RE is now in circuit. Ne? So, how do I get rid of this problem? R accent E changes with temperature and IE. Although I get maximum gain, it's of no use to me. But if I include RE, what have we seen happen to the voltage gain? Becomes 1,7 something. Ne? Down from 152 in this example. Okay? That's also not a very good situation. Doesn't amplify much. So what we do is we use a method called swamping. Now the method called swamping is shown there in figure 618. And what happens? They split the value of RE into two resistors. Can you see RE1 and RE2 now? Say for instance I had a 1 kilo ohm RE. I can now split it into two 500 ohm resistors, and then I would still have 1 kilo ohm for my DC signal. Don't you agree? Because I know my capacitor blocks DC. Nah. So if my current flows through one 1 kilo ohm resistor or two 500 ohms resistors, it remains the same, isn't it? But where's the difference? The difference is when I'm looking at my AC signal. What happens with the AC signal? Remember, the AC signal, capacitor acts as a short. The current's going to flow through there. Nah. But now it has to flow through RE1 and then there. So I'm only bypassing RE2. So what am I doing? I am increasing my voltage gain again by making the value of RE half less than it was. Okay, so what am I doing? Remember, R accent E, unstable, very small resistance, but with a big resistor, no problem. Voltage gain is stable, but that big resistor is too big. I want to increase my voltage gain, so I'm splitting the value of RE into two. So I have now RE1 also in my formula there, which is now only 500 ohms and not 1000 ohms anymore, and I get a bit more voltage gain. Now I've got a stable circuit and I have increased my voltage gain a bit. Alright, that is why we do swamping. Okay, so if we go and look at the example on the next page there, example 6.7, now by using swamping, I can see here now in this specific example, I've got two resistors of 330, 330. So now the total resistance for my DC analysis is still 660, but for the AC part it is only 330. So now my voltage gain at least increased from 1,7 to 10. It's still not excellent, but it's much better than it was. And now I have a still stable circuit. Okay. Please mark the sentence there on top of the page, on page 272, equation 6.8. They say there, if RE1, this is another rule of thumb. Fortunately, every time it's a 10 times rule of thumb. If RE1 is at least 10 times larger than the value of R accent E, then the effect of R accent E is minimized and the approximate voltage gain for the swamped amplifier is then RC only over RE1. Okay. So let's stick with that rule of thumb. Everybody uses the same book. Then we can just simplify this formula to RC over RE1. But please, you have to keep in mind, if I go and look at example 6.7, there is no load resistor. Again, if there's a load resistor, then I have to calculate R, lowercase letter c, which is RC in parallel with RL, which also influences my voltage gain, of course. Alright, just below example 6.7, they mention the effect of swamping on the amplifier's input resistance. Just by showing you how these changes also influences other formulas. Remember now, equation 6.9, we had R in at the base was, if there was no bypassing, it was beta AC times R accent E plus RE. But now look in this case, because now I'm bypassing RE2, I only include RE1. So it influences my input resistance as well. So you have to look at the circuit right from the beginning when you calculate the input resistance to see if swamping is applied, because it influences those formulas as well as already. Okay. Okay, then you can mark example 6.8 NB, 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 because this brings the whole common emitter amplifier, the whole thing together. If we can do revision quickly through so that you can, but you must go and do it more thoroughly at home. So there's my circuit, the complete circuit. If I go and look at example 6.8, I can see that I have a common emitter amplifier, because the input is applied at the base, the output is taken at the collector, so the emitter is on AC ground. Common emitter amplifier. What do I also see? I also see there is a load resistor. I also see there is RS. So I have to calculate attenuation. I also see there is swamping applied. Okay, so remember now I have to adapt my formulas accordingly. What is the first thing that I do when I get a circuit like this and I have to do the AC and DC analysis? Let's start with the DC analysis. The first thing that I do is I draw the DC equivalent circuit. Because of the capacitors, blocks the capacitors, what I'm left with is this. Alright? Then I can do all my DC calculations, which you will find there on page 273. Very first thing that I always do is I calculate what? Input resistance. Why? Loading effect story, I must check if the input resistance is at least 10 times larger than R2 because of the loading effect. Then I decide which formula to use. I can calculate all my DC quantities. Then I go and do the AC analysis. Now remember, the capacitors now acts as shorts and as well as the DC voltage. When I simplify it, there is my equivalent circuit for AC. Now I can see R1 is in parallel with R2. Note what the resistance is at the emitter. And I can see that swamping is used, so only RE2 is bypassed, RE1 is still left in the circuit. Okay, make sure about that, and I can see there is a load resistor, so RC is in parallel with RL. And I can do that calculation as well. Okay, then I have to go and do what? Very first thing that I will do is I will calculate R accent E by using what formula? 25 millivolts divided by IE, which was a DC quantity that I've calculated first under the DC analysis. Alright, then Remember, I have to calculate the total input resistance, but first I have to calculate the input resistance. After I've calculated the input resistance, then I can calculate R in total. Just note that the input resistance in this case, because the swamping used, RE1 is still in the circuit, it's going to be beta AC times R accent E plus RE1. Right, then R in total. What if I also seen RS is available? What does RS? If RS is available, I know what? Attenuation. I have to calculate attenuation because not all of this 10 millivolts is going to get to there at the base. It's going to be attenuated. I'll have to work out that ratio. It's going to be a value of less than 1 that I have to multiply with my voltage gain. Alright, how am I going to calculate the voltage gain? The voltage gain is equal to what? In this specific case, voltage gain is going to be equal to what? If I look at this amplifier, it's R, small c, lowercase letter, because RC is in parallel with RL. What's going to be below the line? RE1, because we assume, we will check it eventually, of course, that R accent E is 10 times smaller than the value of RE1. So once I've got that, then I multiply it with my attenuation, which is a value less than 1. And then I've done my whole AC and DC analysis. And then the very important, I would say the most important, is what you're going to show me in the lab, is the output signals and the input and output signals simultaneously, part C. Very important to show me on the oscilloscope. You've done the oscilloscope in electronics 1. I'm going to ask you these questions theoretically as well. I'm going to give you some voltages and you have to going to draw these waveforms for me via with a frequency as well. Okay? And you know you have to display a waveform as large as possible, and for frequency wise you will show me between 1 and 2 cycles. You're not going to show me 100 cycles on the screen, that won't be accurate. You're going to show me between 1 and 2 cycles on the screen, then you will get your marks. But most important is, of course, when I go and measure at the collector, total collector voltage there in the A part, I can see that these are superimposed voltages because I have a DC quantity at the collector. So in this case, VC already is 4,74 volts, and then my amplified signal will be riding on top of that. Superimposed voltages, you will go and show me that in the lab as well. And then lastly there, it shows me the input and output signals simultaneously. I can see my input signal Vs is small, and my V out is bigger, it's amplified, and it's 180 degrees out of phase, as we have discussed in the previous lesson. Very important, go through this, make sure that you understand, and go and do the basic problems. You will see there are basic problems related to this. Then just the last few things, the current gain. You can underline the first sentence there. The current gain from base to collector is IC over IB, or we use beta AC. If we don't have beta AC, we use beta DC. That's the current gain. Okay? However, the overall current gain of the common emitter amplifier is IC over IS, and I can see IS is VS over RS plus R in total. You can go and look at that. But for our calculations, we will just use beta AC, or if we don't have beta AC, we will use beta DC. Alright, and then the last thing on the next page is the power gain, page 276. Overall power gain is the product of the overall voltage gain A accent V. Remember, we've calculated voltage gain, and that was R whatever C over R accent E or whatever, that was voltage gain. As soon as I multiplied, or I have attenuation available, and I multiply this value with the attenuation, then it becomes A accent V. That means it's the overall voltage gain. Alright? So here you will see they talk about the overall voltage gain A accent V, and the overall current gain AI, which we will use beta AC or beta DC. Then you can see equation 6.11 says voltage or the power gain is equal to overall voltage gain times the current gain. But of course, if I don't have attenuation, the power gain is just going to be voltage gain times the current gain. Because if I don't have attenuation, I cannot calculate overall voltage gain. Then I will just use voltage gain. Alright, so this is the end. Read through the section discussed. Please take note of this. Work through the examples in this section. Do the relevant true-false quiz, circuit action quiz, self-test questions at the end of this chapter, and do the relevant basic problems, which the ones that you are remained with are basic problems 10 to 19. Now this is very, very important, that you go work through the section, do these problems, so that you can discuss anything that you don't understand with me in the next, before we do the next lesson. I will give you the opportunity to ask questions before we carry on with the next work, which will be the common collector amplifier. But I want you to make sure that you understand the common emitter amplifier first. Thank you, ladies and gentlemen.